So this you can see I have given here is the hint. So you can consider a real valued function defined as f of x is equal to sin x and take a is equal to the open interval 0, 3 pi. And then you check whether this condition holds good or not. Of course, the function f of x is equal to sin x is a continuous function. So you can see this one. Now, here is again I have another statement. So give an example to show that the following statement does not hold. That is to say, here is the other way that the function is continuous if and only if the interior of this. Now keep in mind, here I am not putting this way. Okay, I am putting in this way. So here is the interior of f of a is a subset of f of a interior for all subsets of x. Okay, here is you must keep in mind we are taking this here is this for this is if I replace this inclusion by this one, then the statement is not true. Okay, so we must take this one. So here is keep in mind here is this the statement is interior of f of a is a subset of in f of interior of a. So give an example to show that this statement does not hold good. So this statement does not hold good. Okay, for that here is I have already provided the solution. So the solution is the following. So suppose f is a continuous, f is a function from R to R defined as f of x is equal to 0 if x is rational, f of x is equal to 1 if x is irrational. Then of course this function is not continuous. And we can see that f of a is the subset of the set consisting 0 and 1 for all subset A of x. And then we will see that the interior of this, the interior of f of a is equal to empty set. And so the interior of f of a must be a subset of f of a interior. This holds for all subset A of x. But for the converse, now define a function f from R to R as f of x is equal to mod x. Okay, and consider the set A consisting the rational numbers in the closed interval -2 to -1 union all the numbers in the open interval -1 to 1 union irrational numbers in the closed interval 1 to 2. Then the interior of A is equal to the open interval -1 to 1. And therefore, the f of interior of A is equal to the closed interval 0, open interval 1. But f of capital A is 0, closed interval 0, 2. So, the interior of f of A is equal to 0, 2. So, this is the example to show that this implication does not hold good. So, now as I'm mentioning here is whenever we put any, we need any counter example, we always try to see a function from Rn to R, from R to R, or from a function from a discrete metric space to another metric space, or from a metric space to a discrete metric space. Okay. Now, look here is it's very interesting that here is again we have the exercise. Let x, y be metric spaces. Then prove that the function f from a metric space x to another metric space y is continuous on x if and only for every subset b of y. The closure of f inverse b, okay, the closure of f inverse b is a subset of f inverse closure of b. So here is we have the inverse. Okay, so this we can prove again by using the previous result. Okay, so let f be a continuous function, and we can treat that f inverse b is equal to a. Okay, then by the previous theorem we can say that for every subset a, so this is a subset, okay, so this is a subset of okay, so this is a subset of x. So for every subset of x, f of closure of a is a subset of closure of f of a. But f of a, from here you operate f both the side, then f of a is a subset of b. So f of a is subset of b. So closure of this is equal to the closure of this. Okay, and so this is a subset. This is a subset of this one. It means that the f of closure of a, from here it is a subset of closure of b. And now operate f inverse both the side, and then we will get this one. And then you can take so a closure of this. So the closure of this is a subset of this one. So we have this one. Conversely, you take suppose this inclusion holds good for every subset b of y. Okay, then we have to prove that the function is continuous. So let f be a closed set in y. Okay, then we will have to prove that the inverse image of closed set is closed. So since this is closed, it is equal to the closure of f. And by the hypothesis, f inverse f for any subset, this, okay, is a subset of this. But this is your f, so this is equal to f inverse. So it means that the closure of f inverse f is a subset of f inverse f. But this is always a subset of this one. And therefore, this is equal to this one, and hence f inverse f is closed, and therefore the function is continuous. So we have proved that the function is continuous. Now here is again similar to the closure, we have little bit different. So if f is a function from a metric space x to another metric space y, then prove that f is continuous on x if and only if for every subset b of y, f inverse of interior of b is a subset of interior of f inverse b. So what is the difference here and here? You can see here is this, here is the closure of this is a subset of this one. But if you take the interior here, okay, and you take the interior here, then the inclusion will be reversed. So here is f inverse interior of b is a subset of interior of f inverse b for every subset b of y. So you can see here because we know that, so you can prove very easily this statement by using the previous statement, or in other words you can prove directly. Suppose that f is a continuous function on x, but f be any and let take capital B be any arbitrary subset of y, then interior of b is an open set, okay, and f is continuous. So inverse image of open set is open, so this is your open, and therefore this interior of this must be equal to this one. Again, the interior of this is subset of this one. Operate f inverse both the side, we will get this one, okay, and then operate the interior of both the side, we will get this is equal to the interior of this one. And this implies that the f inverse interior of b is a subset of this one. Okay, so this is proved. Now to prove the converse, let us take G be any open set. Okay, then the interior of G is equal to G. By the hypothesis, this is holds good. But this is equal to what? This is equal to this because G is your open set, so it is equal to this. But this inclusion holds, the reverse inclusion holds, okay, always. So we have this is equal to this one. It means that this set is your open set. So inverse image of open set is open, and therefore the function is continuous. So this way we can prove that the function is continuous. Now here is if let X be a metric space and for each I runs from 1 to n, Fi's are functions from a metric space X to R be continuous. Then prove that the function f defined from the metric space X to Rn in the following way, that f of x is equal to f1x, f2x, fnx, then this function is also continuous. Okay, this you can prove by using the definition of the definition of epsilon and delta. So you can try, and then the proof is already given here. I am not going to give this detail of the proof here. You can try if you did not get the answer, and then you can check here. Of course, the second exercise is the following, that if X is a metric space and f is a function from X to Rn, that is to say the converse of the above exercise, which is defined in this one. Okay, and if f is continuous, if this function is continuous, then each component is also continuous. So here is, I have given the hint. Okay, so you can try this by yourself. Now there are several other exercises, and you can also see these exercises. So first, let Rn and R be cubed with the usual metric, then show that the projection map. So projection map Pi, keep in mind the projection map Pi from Rn to R is defined by Pix is equal to Xi. So usually this is, you can treat this as a definition of a projection map from Rn to R. Okay, so this is defined as Pix is equal to I. So all the projection maps are continuous functions. So this you can prove very easily, very simple. Let x, y be metric spaces, f be a function, then the graph of the function. You can see that the graph of the function is defined in this way, that is, graph of the function is the set of all points x, y such that y is equal to f of x. So if f is continuous, then the graph of the function is closed. Okay, this you can prove very easily. Okay, how will you prove this one? You can prove this is closed. You can consider, I am just giving the hint, you can consider a sequence. Okay, sequence converging to a point. So what kind of the sequence here you will take? You will take the sequence like this. Suppose you can take xn, yn is a sequence in the graph of f, such that xn, yn converges to xy. It means that is xn converges to x, yn converges to y. Then you will have to prove that from here x and y lies in the graph of f. That is, you will have to prove that y is equal to f of x. So it can be proved very easily. So this way, you can prove that if the function f is continuous, then the graph of the function is a closed set. Now we show that, provide an example to show that the closeness of the graph of f does not guarantee the continuity of the function f. That's very important. Now the second thing is, if f and g are two continuous functions from a metric space x to another metric space y, then the set consisting elements x in x such that f of x is equal to gx, okay, is closed. In particular, you can see that the set of all points x in x such that f of x is equal to x is closed. So this you can treat this particular case you can treat if G is the identity map. From here you will get this one. And again, this you can prove by considering the sequence. So it is very simple. But how will you prove? You can take a sequence xn. Okay, you can take a sequence xn in this set. Let me call this set is equal to my set is this set is equal to A. So this is in A. Then what will happen? This set is in A. Then f of xn is equal to g of xn. Okay, but the function is continuous, and we have to consider this sequence xn converges to a point x, and we will have to prove that x is in A. X is in A, that is we have to prove that f of x is equal to g of x. So because xn is in A, so f of xn is equal to g of xn. But this, because the function is continuous, this converges to f of x, and this converges to g of x, and therefore they are equal, and so x is in A, and therefore the function set is your closed set. So this way you can prove. Okay, so this you can prove. I am just removing this one, and okay, so this way you can prove this. Okay, so here is I have already given the proof, so you can see. First you try to prove by yourself. If you could not succeed to prove by yourself, then see the proof is here. Now, if x and y be metric spaces and D be a dense subset of X, okay, and f and g are continuous functions such that f of x is equal to g of x on the dense set X, then prove that f is equal to g, f and g are equivalent on the metric space X. That is to say, f of x is equal to g of x for all x is in G. That is to say, if f and g, so here is you have two functions. So suppose so suppose you have a function, this is your x, and you have a metric space y, and you have a function f, you have a function f from two functions f and g, two functions from x to y, such that the value of the function, and D is the dense set. Okay, this is your dense set. Dense set, the value of this function. So here is you will get f of x is equal to g of x. So when x is here, then the value is equal to same. And then if this is true, then it is also true you can extend these functions on the whole space. So that is to say, f of x must be equal to g of x for all x is in capital X. So this is it's a very nice result, or you can see nice exercise, but it can be proved very easily. So here is I have already given this short proof, and you can see that whether you can do it by yourself or not. And then I have another exercise which says that if f is a continuous function, real valued continuous function defined on a metric space X at a point X in F, and if f of x is not equal to 0, okay, then there exists a real number r is greater than 0 such that f of y is not equal to 0 in the, for all y in the open ball with center at x and radius r. Okay. That is to say, if this is, then there exists an approach such that and the function gy is equal to 1 over f of y from the SRX to R is continuous in XR. Okay. So, if f is a continuous function from a metric space X, real valued continuous function on a metric space X is continuous at a point X, and f of x is not equal to 0, then prove that there exists an open ball around x such that the value of the function at the point in the open ball around x is also not equal to 0. And not only this, the function which is defined as gy is equal to 1 over f of y from the open ball with center at x and radius r to r is continuous at x. So, this is continuous at x. This you can prove also very easily. Okay. So, now I stop over here, and in the next talk we will discuss Eugen's lemma. Thank you very much.